Presented by Caltech.
We're on our last major topic, which is dispersion. And we looked at the two different notions of velocity, the phase velocity and the group velocity. The essential point is that the velocity is frequency dependent. The velocity of a wave is a frequency dependent. So in particular, if we have something like kind of a wave packet that's propagating along, if different frequencies are propagating with different velocities, then whatever this wave pocket looks like at one time will look different at a later time because it's made up of many frequencies. And each frequency is propagating with a different velocity. And so the net effect of that tends to be that at some later time, it'll get more spread out. The wave will tend to disperse, if you like. So the last demonstration we have is this one over here. This is a steel wire with a rather heavy weight on it. And I can pluck the wire and see what happens to the wave on it. So plucking the wire is like I'm taking a wire and giving it some initial condition like this. So in practice, of course, this isn't completely sharp. It's, if I blow it up, it's something a little broader because I can't make a very sharp bend. But there's another feature that's going to come in here with a steel wire like this. I'll get my ordinary normal mode frequencies, except that if I try to make a sharp bend in it like this, there's going to be some additional nonlinearity in the restoring force. It's going to resist getting bent really sharply. And that resistance is stronger than say, the other damping forces that we might have. And so that is going to affect my wave equation. So let's just do a simple model for this. Let's suppose that we have a wire like this. We'll put a coordinate system on somewhere. So this bend here is just y of x at time t equals 0. That's my initial condition. And I'm saying that y dot at x and t equals 0 is 0, so I'm starting it out at rest. So I'm just going to kind of pluck it and let it go. And so you remember the example in problem 32 in the homework where you did a Fourier series expansion of this and found out, and the expansion involves many normal modes. And so the expansion of something that looks like this, you expect it's going to take many normal modes. So many normal modes are going to be excited. But there are additional effects as well, in particular the stiffness that I want to discuss. I mean, there's the interaction with the air in the room and the reverberation off of the walls and everything. So you'll hear some of that maybe. But I want to concentrate on the particular aspect of the stiffness of the wire. So resistance to bending which I'll call stiffness. So a model for this stiffness is that my wave equation looks like y double dot minus v naught squared, second derivative with respect to x, plus a stiffness term. So this would be just our ordinary oscillator that we're exciting here. I could, I could add other features, but a simple model for the stiffness is that I have a term with a high derivative, and so I'll put a fourth derivative in here. So so this is the second derivative with respect to position. I'm going to add a term with a fourth derivative. You can ask yourself why I do use a third derivative. Yeah. Oh, okay, so f dot is df by dt. F prime is df by dx. Or I should use partials here, I guess. I should express those as partials to be really clear. Well, but basically that's the difference. And so the high derivative means that, I'm going to get a very strong force that's resisting a real sharp bend. Because the fourth derivative is going to be very big in that case. So at low frequencies, there are only gentle bends in my wire. If I think about standing modes, the standing mode with a low frequency is a very gentle bend. Okay? And so at low frequencies, this term is not going to be so important. Okay? At low frequencies, I'll just get these two terms as the dominant terms. So omega naught is just V naught times K. So that's the expected low frequency behavior. But at high frequencies, the stiffness term becomes important. So in that case, we have to include the alpha y for derivative term. So let's do that. Let's just try our usual solution, oscillatory solution, y equals e to the I kx minus omega t. And I'm just going to plug that trial solution into my wave equation. If I do that, then the first term gives me a minus omega squared. The second term will give you a minus v naught squared times k squared. Bringing down 2 powers of k. The last term is going to bring down 4 powers of I times k. I to the fourth is equal to 1. And I get k to the fourth, so it's going to be plus alpha k to the fourth is equal to 0. So now my dispersion relation is the relation between omega and k. So omega is a function of k, so I can deduce the dispersion relation from here. So the dispersion relation is omega is equal to the square root of v naught squared k squared plus alpha k to the fourth, or you can bring it out an overall k and see what's left. So I can calculate now the phase velocity and the group velocity from this. And it's easiest here to do them as a function of k, since that's what I have, is everything is a function of k, but you can translate it into a function of omega as well. So the phase velocity is just omega over k. So I can write that with a factor of v naught out front, and then a 1 here because I'm dividing through by k squared inside here, plus an alpha k squared over v naught squared. So in the limit of very small k, of course, this just goes to v naught. But I can make the first order correction that this goes like v naught times 1 plus alpha over 2 k squared over v naught squared, just approximating that square root with the Taylor series, with the first two terms of the Taylor series. But it's approximately v naught. So that was my statement here, that basically at low frequencies, I have omega is v naught k. For large k, this term becomes greater than 1. If it's much greater than 1, I can write this as, well, the v naught will cancel. I'll get a square root of alpha. What do I get? A square root of alpha times k. And I could express k in terms of omega too if I wanted to, but we see that v phase is now dependent on the wave number and hence dependent on the frequency. And in this case, it gets bigger as k gets bigger. The frequency goes up. So V group is d omega by dk. So I take that expression up there, take its derivative. So it'll be a half that comes out. It'll give me a 1 over 2 omega in the denominator, and then I have to take the derivative of whatever's inside the square root, which is 2 v naught squared k plus 4 alpha k cubed. So instead of writing omega here as a function of k, I've just left it as omega. Okay. So for small k, this term will dominate over this term. So for small k, it's going to go like v naught squared k over omega. But for small k, omega over k is just v naught. And so this is like v naught. Again, just to noting that that's consistent with that. So the low frequency behavior with a stiffness term is behaving like we expected it to. V group and V phase are the same thing, and they're independent of frequency as the frequency becomes small. For large K, this goes to 2 alpha K cubed over omega, and let's see, so how do I do this? So that's 2 alpha K cubed. So V phase is that, so let me use that. So the alpha K squared is V phase, so that's, let's see, 2 alpha K squared. So let's see, so that's 2 V phase K over omega. Did I do that right? I'm sorry? V phase squared. Is that what you said? Yes. Okay. And K over omega is just 1 over V phase. So this goes to 2 V phase in the limit of large K. That is, goes to 2 times square root of alpha times K. Okay? But so V group and V phase are not the same thing anymore in the limit of large frequencies. Okay, so let's try our string here. Just got to adjust the volume. You okay, Francesca? Okay. Let's see if that's enough juice. So let me just try plucking this string. Okay? Didn't hurt your ears? So people are going to hear that okay? Could try it again. Went out of whack. See if we captured it or not. Okay, so what we're seeing here is on the left, we're seeing my initial pulse when I pluck it. That pulse is traveling up to the top of the room and bouncing back. If you look at the time that it takes for it to go up and back, sort of the overall pulse time to go up and back, that would be the group velocity. And we measured it yesterday. It's like 160, 180 meters per second, more or less. If you think about the speed of sound in steel, if If you look up the speed of sound in steel, you'll find that it's like 5,000 meters per second. Very fast. And the speed of sound in air is like 343 meters per second or something. But so what gives? I got a different speed. When I look at this, you know, it's taking some 150 milliseconds to get up there and back, and if you take the length of the wire, it's about 13 meters, and calculate the speed, you get something like 150 or 180 or whatever. It's much slower than the speed of sound in steel. Well, what am I doing here? I'm exciting a wave along, it's going transverse along. My pulse is a transverse pulse. I've got an excitation that's transverse. And so I'm just watching the wave go up and back as a transverse pulse on this steel wire, which is not quite the same thing as what they tell you when they give you the speed of sound in a steel wire. That's really what you do when you excite a longitudinal wave in the steel wire. Here I'm just letting the wire wave back and forth. So it's just different. It's not the same thing. So you shouldn't be too concerned about that. Let me try this again. Sometimes it works better with damping, sometimes without. So if you listen carefully, when I first hit it, you'll probably hear some high frequencies, and they'll very quickly go away, and then you'll have the long rumbling, okay? So see if you can hear that initial high frequency going away. Think of it as a chirp. Let's try it like this. You hear that? We'll do it again. If we look at the pulse, this is kind of an ugly pulse, but if you look at the pulse that went up, in this case, looked kind of like a little square wave with some noise on it. And when it came back and suddenly went up, up, and took a lot longer. That's the dispersion going on. All those frequencies in the wave going up have traveled up and down at different velocities, and they've come back down to make something that's looks different and is taking a longer time. So we're seeing the effect of dispersion. We're seeing the effect of the different speeds of the different frequencies. I can try to do this with, so I'm going to just hold the string here. I'm going to put some damping on the string and see what happens. So the chirp might have been more pronounced. But again, you see the dispersion. The pulse, the initial pulse is kind of up and down and restored to the baseline very quickly. And by the time it goes up there and bounces back, it's spread out much wider. So again, we've got a nice illustration of dispersion. Okay, that's probably enough for that. If there are any questions on it. The weight on the wire so that it doesn't stretch too much. It's a heavy lead weight that's on it. Okay, so not unrelated to this is an important theorem in communications and in waves in general that I would like to share with you. It's a theorem called the bandwidth theorem. And the text has a qualitative discussion of this, so kind of a hand-waving discussion of it. But I want to make it much more quantitative. And so again, let's consider a wave packet. So for example, it might look like what I drew over there, or something that's a little bit like what we saw in the scope, that wave packet traveling along. And we see from dispersion that can change its characteristics as you go along in time. So I could draw this either as a function of time for some position or as a function of position for some time. Let's suppose this is a function of position at some time. It might look rather similar either way I look at it. Okay. So this can be decomposed into Fourier waves. That is, into a Fourier sine and cosine series. Let's see, I'm going to go over there. So this would be a Fourier series of a superposition of monotonic waves, of monochromatic waves, that is. That is, waves of well-defined frequency. And most generally, I can do this for periodic waves if my pulse happens to be periodic. For periodic psi, say, so psi is what I'm calling the amplitude of the wave. So psi of x is how far up and down it's going as a function of x, if you like. So for periodic waves, we know we can expand in Fourier cosine and sine waves. So at the most general level, there could be a constant term plus an expansion in both cosines and sines. It all depends on the boundary conditions. For different boundary conditions, you'll get different contributions from cosines and sines. And so A sub n and B sub n are here. I've only written down the time dependence. The A sub n and B sub n are in general functions of x in doing this expansion. So, as I said, the text makes a qualitative discussion of what the width of such an object is in position compared with the width of such an object in time. So you look at the variation of this in position, you look at, how wide is this pulse in position, call that delta x, and then you do the same thing as a graph as a function of time for some x, and you get some delta t. And they argue that delta the width of any such pulse in position and time is of order 2 pi. But this is what I want to make more quantitative. I want to show you that you can actually derive what the real condition is, and it's an important condition. It's a feature of waves that permeates many, many things. It's going to get a little mathematical, but it's important mathematics anyway, so I don't feel too bad about it. It's basically kind of telling you that the sharper it is in time, the wider it is in position. Or the sharper it is in position, the wider it is in time. That's the basic idea of what the bandwidth theorem is telling you. If you make something narrow in position, you're going to have to put many frequencies in to make it narrow in position, and those many frequencies are going to make it, well, actually I should say it the other way. If you have to do a sum over many frequencies, then it's going to make it wide in terms of time. Okay, let's actually see how that works. Maybe that's not so obvious. So what are delta x and delta t? What do we mean by those? So to get something that's more quantitative, we need to define these. So we need to have some idea, some way to measure the spread of a wave packet. We can't quantify it if we don't know what delta x or delta t mean. Okay. So physically, it makes sense to consider where the energy is. So if the amplitude is psi of t, say, suppressing the x dependence for some x, then as we've seen, then the energy goes like the square of that, or the intensity goes like the square of that. For example, if the amplitude, if we're describing a light wave, then the amplitude is described by how big the electric field is, and it's the square of the electric field that gives you the energy density in your wave. Okay. And on our string, when we did our strings, we saw that the energy went like the square of the amplitude of the motion of the string. So the energy is proportional to, or the energy density is proportional to the square of that. So I want to define my spread, my spread in t, say, my delta t, in terms of psi squared. So for convenience, I'm going to use units such that, if you like, the total energy is equal to 1. I'm going to use units such that the integral of my energy over time, or my energy density, or my flux over time, is equal to 1. So if I come out with it being 5 joules, I just define my energy unit to be 1/5 of a joule, to be 5 joules. And I get 1, 5 joules. Okay, I don't have to do this. I could carry along always dividing by this quantity in all the equations I write, and we get the same answer in the end. But it's a lot easier, it's a lot more convenient not to have to keep writing this integral. So I'm just going to choose my units such that it becomes simple. If you like, you can now think of this as psi squared as a probability density. Okay, so let's see. So the average time of the pulse so what's the average time? So I want to take and get the average of t. Okay. Oh, I still have a board, I think. So I'm going to use a bracket like that to denote an average. That's kind of a physicist's notation. So what's that average? That average is just t psi of t squared dt. Of course, it's all divided by psi of t squared dt to actually take the average. But I said I'm going to make that the denominator equal to 1. I'm going to assume that's 1. So I don't have to worry about that denominator. So that's just so that's my average. It's the average time of my pulse. So I'm going to do something else for convenience that I, again, don't have to do, but it sure makes things a lot simpler in the writing. I am going to take my t-coordinate, and if this expectation value of t is non-zero, I'm going to shift my coordinate by that expectation value. So I'm just going to redefine my coordinate such that so that expectation is just 0. And I'll just simplify my calculation as I go along. Okay. So that has nothing to do with the spread of the wave packet. So you may be wondering why I'm doing it. I want to calculate the spread. Well, so for the spread, a natural measure of the spread of some function is its variance, or the square root of the variance, which is the standard deviation. And so let me do that. That is, I'm going to take the RMS spread, the root mean square deviation from the mean. So the variance is just the square of that root mean square, so the variance is just the mean squared deviation. So I write that so I don't have to use square root signs too much. So that's t minus, so I'm taking the deviation of t from the mean, squaring it, and I'm taking the mean of that quantity. It's the mean of the squared deviation. Okay. And so that's just equal to the integral from minus infinity to infinity. So this expectation value, this averaging, is just t minus average t squared. Of course, that average t is going to be 0. Psi of t squared dt. So that's by definition what the variance is. And with with t equals 0, expectation value of t equals 0 implies the variance of t is just integral minus infinity to infinity of t squared psi of t squared dt. So it's a lot simpler to write. Okay. And so the punchline is I'm just going to let delta t, so I'm going to let my measurement of the spread of the wave packet, delta t, I'm going to let that be just the variance of t square root, the root of the mean squared deviation. Okay, so I've got delta t here. Let me think about frequency. So I'm going to end up with a relation between time and frequency here, between the spreads in the two. I mean, I want to define delta omega as the same kind of thing in the frequency, in terms of the frequency distribution. So I have many frequencies going on, making my pulse, and it's making the pulse of some width. The narrower I make that pulse, the higher frequency components I'm going to have. And so the narrower I make that pulse, the wider I'm going to tend to make my frequency distribution, because I have to add more and more higher frequencies to make the pulse narrower and narrower. So it's going to make sense that we're going to have some relation delta t times delta omega is equal to something. So what about the variance of omega? I need to estimate that. So I've been glossing over something here. I said that we could, do I still have it? I must still have it. I've just covered it up somewhere. I said here, for a periodic function psi, I can expand and assort Fourier sine and cosine series. And that's the most general form of my cosine and sine series. The constant here just corresponds to the n equals 0 term for cosine. I really don't want to deal with a periodic psi. I want to make a pulse that I just make and send out. It's a one-time pulse. I just want to analyze what happens for a pulse. I don't want to really have a string of pulses to worry about. So I want to do something to this that works for a string of pulses, not a periodic, that works for a single pulse, not a periodic string of pulses. So I'm going to have to take some kind of limit on the period of that, on the period of of the fundamental period of this thing. Let's see how it works. So let's first of all, to do this, let's make things a little simpler. Let's rewrite our Fourier series as psi of t is equal to the sum from n equals minus infinity to infinity of a sub n e to the I n omega naught t. This is exactly equivalent to this, except I've relabeled a sub n. So this a sub n is both a sub n's and b sub n's in some linear combinations. But this has all the same terms as this does. You can just write this as cosines and sines, or instead you could write these sines and cosines as exponentials. I've gone from minus infinity to infinity, so I have both cosines and sines and all possible combinations. So it really is just a rewrite of the other expression, which you could demonstrate for yourself. And it's simpler to work with. So this expansion, this is for periodic functions. With period, we'll call the period t. And what's t? Well, t is 1 over the frequency in cycles per second, but that's just 2 pi over omega naught. So this function is periodic with period t equals 2 pi over omega naught. And I said I don't want a periodic function, so I want to let t go off to infinity here. I want to take the limit of this as t goes to infinity. So let's start that process. I don't think I will finish it today, but we'll get somewhere along. So let's see. Let's first of all just rewrite this. Substituting in what omega naught is. Psi of t is equal to the sum from n equals minus infinity to infinity, a sub n, e to the I, well, okay, 2 pi times I, if you like, for the 2 pi there. 2 pi I nt divided by this period t. With what I'll call an inverse relation. That is, I use my orthogonality to deduce what the a sub n's are. So in a sense, I'm doing an inverse of that. I'm calculating a sub n as a function of psi instead of psi as a function of these guys, as a function of a sub n. So just using how I know to calculate these expansion coefficients, I have a sub n is 1 over t times the integral from minus t over 2 to t over 2 times psi of t e to the minus 2 pi I nt over t dt. And this holds because I have an orthogonality relation. And I'll write the orthogonality relation in terms of these exponentials instead of what we did before, which was in terms of cosines and sines. But it's the same relation. 1 over t times the integral from minus t over 2 to t over 2 of e to the 2 pi I nt over t e to the 2 pi I m t over t dt is equal to delta mn, Kronecker delta of m and n. So that's my orthogonality relation that allows me to do this calculation. And so now I want to turn all this into the limit as t goes to infinity. So I want to be able to describe just a single pulse travel. Okay, so this is really where the mathematics is. It's just doing this exercise. There's nothing difficult about it unless you want to be really rigorous, but we're not going to worry about that here. Okay, so we want to take the limit as t goes to infinity. Let's let omega be 2 pi n over t. So we're dropping our notion of omega naught. And let's see, okay. So omega, so t is going to go off to infinity, but n goes everywhere from minus infinity to infinity, so we're going to cover the full range of frequencies. Minus infinity to infinity here. And psi, and I'm going to define something I'll call psi hat of omega. So I'm going to do things a little more symmetrically on this a sub n. I'll multiply this through by t, so I'm going to define basically something that's t times a sub m. And I'll get some kind of a symmetric looking situation between the psi and what I get here. So I'm going to call it psi hat to really label it like psi. So this is, I'm going to define it as t times a sub n. And then for convention, I'm going to divide it by square root of 2 pi. I don't have to do that, and there are different conventions. Not everybody does that. But this is a common convention. It's just a convention, though. It's basically t times a sub n. Then, let me see how much time I probably don't have time. I think I'm going to stop here, okay? So, sorry, I'm not giving you the punchline. We'll have to get to that next time. But we set everything up. And what we're going to end up with is the Fourier transform. And its inverse.